Hello, everyone, and welcome to the AI Agent Frontier seminar. We have a fantastic session lined up for you today. It's my absolute privilege to introduce our speaker, Dr. Graham Neubig. Graham is an associate professor at the Language Technology Institute at CMU and chief scientist at OpenHands. He's a leading figure in our field. His research has driven fundamental advances in large language models, particularly in the application to software development. Beyond his research, he has also made a major impact on the community by making NLP more accessible through open source software and open course materials. I've personally followed his work closely, so it's my real honor to host him today. Today, he'll be sharing lessons from the trenches in building agents for software development. Graham, thank you so much for joining us. The floor is yours.
For sure. Thank you for having me. So, yeah, I'd like to talk about some lessons that we've learned in building usable coding agents, specifically from the point of view of OpenHands, which is our open source software that's used to develop agents that see the world through software. And if you're interested in taking a look at it, you can take a look at the Software Agent SDK, which is where most of the agent code lives, or app.allhands.dev, where you can use it online. The reason why I'm interested in coding agents is not actually specifically for coding, but rather because coding can be used as a means to an end, as is kind of outlined by this quote from Mark Andreessen's essay, Why Software is Eating the World. Basically, if you're able to develop software, you're also able to develop movies and agriculture and national defense, all of the other things that you would like to do. And so I'm motivated by the question, if we gave everybody the ability to quickly write software to achieve their goals, what could they do? In particular, one of the things that I'm very excited about is whether software-based agents can advance science. And this is kind of epitomized by the Nobel Prizes in 2024 for Geoff Hinton and Demis Hassabis, for instance, who were people who were not, running particle accelerators or running wet labs, but rather writing software that allows us to model our world and learn more about how it works. So I've had a pretty big personal transition of moving from, doing less programming without agents. So the without agents part is blue to more programming with agents, where this part is red over here. And you can see that the amount of code that I personally have been able to write has increased quite dramatically through the use of agents. And it's just, an example of the productivity gains that you can get through doing this. And as I mentioned before, OpenHands is the tool that we use. It's one of the biggest current open source agents for software development. I would say that OpenHands and OpenCode are the two biggest ones. But it's kind of quite popular from a research perspective because we make it easy to benchmark and other things like that. So if you're doing research on agents, I'd highly encourage you to, take out the Software Agent SDK. It's pretty easy to use. But here I'd like to talk not about the software, but about the lessons that we've learned in the process of creating the software. And first, lesson number one. So lesson number one is believing in simplicity. And this is the accuracy on the popular SweetBench benchmark. And you can see it kind of goes up in fits and starts. So, it goes up a lot and then levels off for a little, goes up a lot and then levels off for a little. And typically, the reason why it goes up a lot is not because of some complex agent code or multi-agent coordination or something like this, but it's usually because somebody trained a better agentic language model. And training an agentic language model is definitely not, easy. It's a complex process. But from the point of view of scaffolding around the agent, you often don't need, a whole lot of scaffolding to get the core capability of being really good at software engineering. And I'm saying this now, and it might seem kind of obvious to some people, but it definitely wasn't obvious nearly 2 years ago when we started developing OpenHands. And Then, if you look at some of the competitors that we had competitors like MetaGPT, which were taking a different approach, which was saying, we have a software company, and then we have a boss agent, a product manager agent, an architect agent, project manager agent, et cetera, et cetera. So instead of that, basically at OpenHands, we have a single agent, but a single adaptable agent. And I'll talk a little bit about adaptation, in a bit. Nonetheless, agents are basically characterized by the tools that they have availability to. And if they don't have the tools to do the job, they won't be able to they won't be able to solve the diverse variety of tasks. And so my philosophy that we have followed recently, and I think has been pretty successful, is that we should generally use tools that were created for human programmers and are flexible. And specifically, what we provide to our agents is a bash terminal so it can run programs, a file editor so it can edit files, and this is kind of analogous to an IDE that is used by humans to edit files when they're programming, a visual web browser so it can browse the web, and then access to API calls that allow it to pull in data that it would not be able to have access to otherwise. And so a default example of this that we provide is a search API. And the reason why we provide a search API is simply because if you go to Google on your web browser, you get blocked by anti-robot measures. So you really need to access through an API if you want to do it, properly. So um, basically, in our default agent, this is more or less all that we provide. And that might seem limiting at first, but when you realize that if you can edit a file and write a program and then run bash over that program, you don't really need another tool to do a lot of things. You can just download a library that you would use in Python and then execute a program with that library in bash, and you're able to do more or less most of the stuff you need to do. And a visual web browser also allows you to view multimodal data, visit websites that allow you to do various things and stuff like this. So this is a research paper called Coding Agents with Multimodal Browsing are Generalist Problem Solvers. And this we did this a fair time ago, so the absolute numbers are low, but basically what we demonstrated was this very simple recipe, OpenHands Versa on the top, was able to outperform many much more complex state-of-the-art methods at the time. And of course, these numbers go up with language model performance, but I think the general thesis still more or less stands. So another lesson that we've learned is code don't click, except as a last resort. And this is based on our paper Beyond Browsing API-based web agents. And there's kind of two paradigms of agents nowadays. One is coding agents like OpenHands or Claude Code or other things like this. And then there are computer use agents, and these are things like OpenAI Operator, which maybe fewer people have heard of. Um, the or use right now anyway. But basically, the difference between them is when given a task, open the latest commit log by user Amy that has failing tests. The computer use agent or GUI agent or browser agent would go, go to a website, search by clicking on a search box, clicking various links and stuff like that. In contrast, if the same data from that website is available through an API or available through an MCP, you can just write a program to call that API, and you will be able to do a good job. So on the other hand, there are some cases where the stuff that you want to do is just like not at all available through an API. So like if you're working with a website or working with data that doesn't have APIs available at all, you might still need to, use the standard API GUI-based transaction method. And so basically what we did was we took a browsing agent that just did browsing, an API-based agent that just called APIs, and a hybrid agent that called both of them. And here are the results on the Web Arena benchmark. So the Web Arena benchmark was a benchmark that was created for web browsing agents. And because of this, all of these tasks should at least theoretically be able to be solved by the browsing agent. But what you can see is the browsing agent, its accuracy is actually quite low. Um, but if you switch from the browsing agent to the API-based agent, you can essentially triple the accuracy or double the accuracy in many cases. Um, However, in some cases, you cannot, and the accuracy goes down or it just doesn't rise by very much. And perhaps unsurprisingly, the reason for this is because the APIs that are available on some of these less sites where the API-based agent is less effective were just kind of poor. And so in that case, you can combine together the browsing agent and the API-based agent and get it to, do a much better job by combining together those two traits. And specifically for the hybrid agent, we prompted the model to use APIs in except in the worst case where no API was available. We also did an intervention where Reddit in particular had very poor APIs and that didn't allow you to do many of the tasks. So we took the 18 APIs that already existed, added 13 more to cover kind of the very broad task categories that needed to be done in order to solve many of the Web Arena tasks. And this essentially doubled the accuracy there. And so what this indicates is if you have good APIs or if you're able to create good APIs, you should be able to improve this accuracy and further improve the overall scores that you can get with an agent. And so my conclusion from this basically was, there's a lot of interest in GUI-based agents, but really GUIs are built for humans, and language models are quite good at writing code, and that's often more efficient and more effective. So, code don't click, except in the case where you really, really need to. And I'll also talk about how we can automatically induce APIs in a little bit. A third lesson, which I've already alluded to at the very beginning, is agentic training is essential. So, like as I mentioned with respect to SweBench, a lot of the very large gains that we see are due to agents being trained or language models being trained to be good as agents. So what does it mean for a language model to be good at being an agent? An agentic LM must have good instruction following ability. So if you tell it to do something, it will do it. If you tell it not to do something, it won't do it. And it will continue to be consistent in following those instructions, even after a very long trajectory of taking actions. It also has to have tool use and coding abilities. So if it is given tools, it should be able to comprehend how to use them and call them properly. And for code, it needs to be able to write, like Python code or Java code or whatever code in the language that you would like. It also needs to have environment understanding. So if you're trying to understand multimodal data, it needs to be able to, fully comprehend all the stuff you need to pull out from multimodal data. It needs to have error awareness and recovery ability. So some of the older agentic or older language models that weren't trained very well as agentic language models, one of their big failure cases would be that they make a mistake and then they just continue making that mistake over and over again, and they aren't able to, for example, try a different strategy. And so this is something that we can fix as well. And then finally, reasonable cost. So we'd like them to be, not too expensive. So how do we get there? There's basically three major methods for training agentic language models, or getting data to train agentic language models. The first one is maybe the most popular and prominent one right now, which is reinforcement learning. And the way you do reinforcement learning, of course, is you have an input and then you have a way to receive a reward. So in the case of software engineering, your input might be something like a issue on GitHub and a code base. And the way you get the reward is by implementing a patch to the code base that resolves the issue. And then you take the unit tests that are associated with the issue and you see if the unit tests pass. And if so, you get a reward. and you backpropagate that positive or negative reward back into the LM-based agent. And there's a fair number of papers on this nowadays. Our paper SWEGEM was probably one of the first papers that explained how to do this sort of agentic training for software development agents. So you can take a look at that paper if you're interested. Tool number 2 is synthetic data. And so synthetic data is especially useful in cases where you cannot easily get the input in the verifier, or in the case where your language model is just too bad to do a good job at the and get like any reward in the first place. And so this is an example from our paper Go Browse, where essentially we do this for web browsing tasks. And the way this works is we take a website, we explore the website, so we walk along the different pages of the website until we get to a particular page. We then use a language model to propose some tasks that could be done on the page. So for example, if you go to the products page, you might get buy product, list product, other things like that. And then you do rollouts with the language model from that page to finish this up, and then you use an LLM as a judge to kind of judge whether it was correct. And then specifically in Go Browse, we then continue exploring from the page that we approached. But the basic idea is you synthesize tasks, you might even synthesize environments, and then you synthesize feedback with the hope that you're able to do that with at least some level of accuracy and generate good training data. The final way that you can collect data is human demonstrations. And so this is an example from the Android in the wild data set, where basically people at Google hired a whole bunch of people to do 689,000 multi-step demos on Android applications. And so I do not use a lot of human demonstrations myself because I don't have the money to hire annotators to do 689,000 multi-step demonstrations on the data sets that I'd like to train on. But this is useful if you're able to collect human data or human feedback in some way, in some cases. But anyway, these are just the categories. And then if you look at each category, there's a lot of different data sets that use all of these sources. So for example, there's Agent Instruct that does coding, API and tool use, and web browsing, or Code Feedback, which does coding through manual means. Agent Instruct is synthetic. We also have rollout data sets and all of these. And so about a year ago, the situation was kind of very chaotic in that all of these data sets existed, but it was very hard to use all of them because they weren't kind of standardized into a standard format. So in order to mitigate this issue, we recently created and released the Agent Data Protocol, which basically is a standardized format that allows you to take data that was created kind of agnostically or created by a bunch of different groups and standardize it into a format with just the right level of specificity. And what I mean by just the right level of specificity is we have a very small number of actions, like an API action, a code action, a web action, a message action. And then we have observations with respect to all of those actions. And these are not overly specific, which means that we don't need to work extremely, extremely hard to get them into this format, but they're specific enough that we can then take the data that's in this format and convert it into the SFT format for a number of agents that we would like to train. So we converted it into the OpenHands SFT format, the SWE agent SFT format, the Agent Lab SFT format. And at this time, I believe we have something like 3.5 million trajectories in this format. So I believe it's the largest SFT data set that there is available for agents. So if you look at the paper, the Agent Data Protocol paper, we have results where we basically show that this improves all of the agents that we trained with it. And also, training on this larger data set is more effective than training on any individual data set for an individual task. So I think this is a very valuable resource if you want to take a model and make it initially good at training, for example, before you start doing reinforcement learning. So, lesson number 4, I'd like to talk about benchmarking next. And this is a very, very interesting problem because I feel like evaluations are often holding our field back. And if we had better evaluations, we could do a lot better. But the problem is, this is not really for the lack of evaluations. There are many agentic evaluation benchmarks, um, but it's kind of hard to design and standardize all of them. There has been a lot of progress with respect to this, for example, by a few places like the Prime Intellect Environments Hub or Harbor. And so I think we're making a lot of progress on this in the open source community, but we're still, there's still work to do. Um, we specifically are interested in software development, and in software development, I'm sure many or most people here are aware of SweBench, which is a very popular benchmark created by Princeton on how to resolve GitHub issues. And this is a great benchmark, but the problem with it is that it only covers um, resolving GitHub issues on Python repositories. And there's a few other issues with it. One other issue is that a lot of the language modeling companies kind of fit very heavily to getting a good score on SweBench. And because of that, the scores on SweBench, I feel, are not like extremely representative of, my overall impression of how good the language model is. So if a model has a really good score on SweBench, that doesn't necessarily mean that if I download it and use it in my software development workflow, it will, like feel like a good model. So our attempt to try to fix this is a new meta benchmark called the Open Hands Index. And basically, it's a benchmark that tries to test some of the core capabilities that we believe are really important to be good at software development. So core capability number 1 is SweetBench style issue resolution. But we also have greenfield development, so creating a whole app from basically zero. And for that, we use Commit Zero, benchmark created by Cornell. For front-end development, we use SweetBench Multimodal, which is the multimodal version of SweetBench created by Princeton. Testing is SWT Bench, and this is basically figuring out whether you can reproduce reproduce issues, create good tests to reproduce issues. And then the final one is info gathering, which is Gaia. And this is not strictly a software development task, but in software development, it's often really important to be able to go out and like research APIs or gather information from the web or process Microsoft Docs or things like that. And so Gaia tests the ability to do that. So this is available at index.openhands.dev, and basically we are constantly updating this with the newest models. So recently we just added GLM5 and Gemini 3.1 Pro. And I'd like to just go through the results kind of quickly because I feel like they're kind of interesting. But the first thing that we have here is a trade-off between average score and cost. And obviously, this is something you'd want to know because running agents can be rather expensive. And so you'd like to be able to find one that has a good trade-off between what you're able to afford and what you would actually like to do. And so here we have Claude Opus, which I think a lot of people will agree is a very good model. But it's also a relatively more expensive model. And then over here we have Minimax M2.5, which is a smaller open weights model, and you can run it for very cheap, kind of 1/8 of the price of Claude Opus, but it still gets a pretty competitive result. We also have runtime versus performance. And so I think this is very interesting. It's how many seconds does it take to finish a task? And actually, Claude Opus is very fast at finishing tasks because it has very good parallel tool calling abilities. So Number one, it gets to the core of the problem quickly. So it quickly finishes the problem, but also it's able to call tools in parallel. So it can do multiple things in a single LLM step. So it's really kind of head and shoulders above the rest. And you can kind of look at the other comparisons there. We have all of the details here. We also have all of the data from all of the runs. And this is useful if you're, for example, somebody who is studying agent um, behavior. So if you want to go in and find a bunch of different language models and study how their behavior changes, you can download all of this data. It's all available on this website here, so you can go and check the results. And we have all of the data in a kind of easy to download format. And then finally, we have like visualizations, but also you can see which model is better at each of the tasks, how the model performance evolved over time, and also the open model accuracy by size. So we tried to break down a bunch of things that we would personally like to know ourselves. So hopefully this is a useful resource. Um, so this is about benchmarking, but benchmarking is not everything. And I use agents myself, and one of the bottlenecks right now is figuring out how agents are actually working together with human users. And so we also have a recent paper on evaluating agents with humans in the loop. And this was done by essentially getting a bunch of users to use the service. So this specifically was through our web service where we had OpenHands deployed. We asked them to rate the agent results. And so this gave us, like a 1 through 5 rating. About 8% of the trajectories ended up being rated between 4 and 8, depending on the month. Um, so this gives us good feedback, but it's also very sparse feedback. So in addition to this, we took an approach where we trained a model to predict ratings based on features that were extracted from the trajectory. So, for example, some things that we extracted from the trajectory were did the user send lots of messages, or did the agent write tests, or did the agent make a pull request, or other things like that. And so what this does is this means that for the other, 92 to 96% of the places where we don't get human feedback, we're able to predict that human feedback from features that exist in the outputs. So the next thing that we want to do then is we want to evaluate different types of agents to see if they are doing a good job when they interact with humans. And over last summer, we did this across a number of both language models and harness design decisions. So, for example, we varied Claude 3.7 to Claude 4, varied Claude 4 with GPT-5. We had a difference between not having any planning and having planning and showing planning. And then also the number of steps that we had in memory before we compressed the memory down to be smaller. And what we eventually found was Claude 4 was rated better than Claude 3.7. GPT-5 was rated worse than Claude 4, and planning was better than not showing planning. And then for memory, we got no statistically significant result. But using our prediction model, we were able to get a more statistically significant result than if we solely relied on human feedback, which demonstrates that there's kind of a utility in looking at all these other signals that we get from human interaction other than just the actual feedback. One other interesting finding from this paper is that benchmark scores sometimes do and sometimes do not correspond with human impressions of whether the model is doing a good job at those tasks. So we took a bunch of different benchmarks, similar to the ones that I talked about in the Open Hands Index, and calculated the delta based on human feedback and the delta based on the benchmark scores, and found the correlation between the two. And for Claude 3.7 and Claude 4, the correlation was quite good. But for Claude 4 and GPT-5, the correlation was not very good. And we dug a little bit more into the data, and what we found was essentially GPT-5 often was more accurate, but the problem was that it was also a lot slower and a lot less verbose. And it's not just accuracy that matters to people. It also matters that, it's able to finish the task quickly and that it is, able to provide updates to the human user at the same time. So, benchmark scores, especially single dimensional benchmark scores like accuracy, are not the whole story. Another big thing that I'm, interested in and worried about is whether we are able to handle vague instructions. And the reason why I'm interested in this is because agents are often given instructions that are not very clear. And so the first step to solve this was to benchmark it. And so we have a benchmark on ambiguous SWE-bench. And what this is essentially we took SWE-bench verified, which is a human verified subset of SWE-bench that's basically not ambiguous. They found the issues that were judged by humans to not be ambiguous. And then we took an LLM and we removed a lot of the necessary details from these issues. And so that resulted in paired ambiguous and unambiguous inputs. We then create a user simulator where the user simulator is provided with the unambiguous inputs. And the agent is given a tool that allows it to converse with the user and ask questions if it's uncertain. And so then we have the this user simulator answer questions. And so if we look at SWE-bench verified scores and ambiguous SWE-bench scores, we can see there's a big drop in the score. But if we give the agent the ability to converse with this user simulator, that drop goes away to some extent, but not all the way up to the top. And what we would like is we would like this orange bar to be, like all the way at the top. We'd like the agent to be able to fully recover in the face of ambiguous instructions. So one interesting thing about our current paradigm is if you can build an evaluation, if you can scale that evaluation, you can then do reinforcement learning by using that evaluation as a reward when you trade models. And so that's exactly what we did. We used the same strategy to make prompts vague. And then we created a user simulator. The user simulator is similar to the user simulator I talked about before, but it has a few small tweaks. The biggest tweak is that we gave a concept of low effort, medium effort, and high effort questions. So a high effort question would be something like, tell me everything you know about this issue. And then the agent would have to say a whole lot of things, and that's not a good thing. But a low effort question might be a single line clarification or something like that. And so our reward function for model training is essentially whether the model succeeded and also whether it is able to ask, like whether it asks high effort, medium effort, or low effort questions, where you get a negative reward for asking a question, but that reward is essentially smaller for low effort questions. And what we were able to demonstrate is we took a 32B model and we trained it with this reward function, and that was able to both improve our task success rate and kind of improve our proactivity and personalization score, which was essentially related to the amount of effort in the questions that were asked. And impressively, I think we were able to make this 32B model outperform GPT-5, which is, of course, a very strong model. So a final thing that I'd like to talk about is that agents should adapt with us. And agents essentially need customization. And our approach, as I mentioned before, is not to create a whole bunch of different agents, but to rather create one agent that is able to adapt in necessary ways so that users can, achieve whatever goals they want to achieve. So one way that you can do this is through agent skills. OpenHands has had a concept of skills, which used to be called microagents for a long time. Now I think like maybe most agents have this sort of ability, but what this is this is the ability to um, pull in textual information about how to solve particular problems into the model. And these are usually specified as markdown files that are put in a repository that you can use. Um, so one way to do this is to specify them manually, but we also have a couple research works where we examine the kind of utility of automatically inducing these skills from data. And the first one is called agent workflow memory. And the way this works is every time the agent performs a task, you can obtain the actions from this task. You can then use a model similar to the model, the success prediction model that I talked about in the previous section, to predict whether the agent did a good job at this task or did not do a good job at this task. If the answer is that the agent did a good job at the task, you then segment the trajectory into workflows, and you add the workflows back into the memory so that the agent can use them next time and reference how to successfully solve tasks of that variety. So this is a first step towards kind of textual skill induction. We evaluated this on Web Arena-based web browsing, and basically we saw a huge boost almost right away as the agent figured out how to do basic actions, but this boost continued to increase as time went on, as it was able to build a more complex and compositional skill or workflow library. But there's a few problems with agent workflow memory. The biggest problem is that even if you're able to induce very complex skills or workflows, you're not able to really improve your efficiency because the agent will still have to take lots and lots of steps. And that's kind of like one of the problems with web browsing agents in the first place, which kind of, you know, is the reason why I suggested we might want to use APIs instead. But the good news is in this work, we actually demonstrated that you can induce programmatic skills where you can actually run the skill and perform the task. And so the way this works is you have a natural language query, you take your currently usable APIs, you solve the query, you then segment them into kind of workflows as you did before, but then you ask the language model to generate code that implements that workflow. And these skills then can not only take a single step, but they can do things like fill and then click. And so this allows you to act more efficiently than if you were just doing each of these steps one by one. And the nice thing about this is if these skills are then validated by testing, you can put them back into your skill library, which gives you more complex compositional skills. So you could actually build up more and more complex programs to solve more and more complex tasks as you learn more and more. And we demonstrated that this is both more effective and more efficient than using agent workflow memory. So that's all I have for my presentation today. I'd like to talk a little bit about some of the major challenges that I'm thinking about at the moment, and we're either actively working on or thinking of working on. So the first is the verification bottleneck. So the verification bottleneck, what we mean by this is basically that we are in a situation where it's very cheap to generate code right now. And when generating code is very cheap, the bottleneck then switches over to being verifying the generated code. And so programmers are spending all of their time in code review, and that's no fun. But if they don't spend all of their time in code review, you end up getting a large bloated code base that doesn't do what you want it to. So, we're kind of stuck. So I actually didn't put this on my slides, but we very recently released this blog post and paper on learning to verify AI generated code. And this is kind of a new evolution of the method for learning from human feedback. Um, I can maybe open the paper because paper is more informative. And the paper is called "The Rubric Supervised Critic from Sparse Real World Outcomes." But basically, it's pretty similar to what I talked about with generating like learning from human feedback. But the main difference that we do here is instead of learning directly from human feedback, we learn from uh, indirect human feedback in the form of whether code that was written by the agent actually survives into the final code base. And what I mean by this is if the agent, did a whole bunch of commits to the code base, and then a human did a commit, and then the agent did some more commits. We can look at how many lines of code written by the agent actually made it into the final code base for that particular segment of work. And if that code survival rate is very high, then the agent probably did a good job. If the code survival rate is very low, then the agent probably did a bad job. And then we can use this supervision signal to train a model specifically to kind of like supervise an agent. And we've also incorporated this into like the OpenHand CLI. So like after you run the agent, it tells you how likely the critic thinks it was successful. And we also demonstrated you can use it for sweep entry ranking, a bunch of other tasks. Um, Another thing that we're thinking about is large code bases. So how do we coordinate a bunch of different agents to kind of simultaneously work on a single code base? And hopefully we'll have some research work on this out in a little bit. Realistic and diverse evaluation environments. So evaluation is extremely important right now, and I don't feel like we're covering all of the cases that we need to cover in order to demonstrate that agents are really good. And as I mentioned at the beginning, I'm pretty interested in AI for science, and so how can we come up with a evaluation environments that reflect both like software engineering and AI scientists in a way that is really realistic. And I don't think anybody has cracked this, and especially people have not cracked this over the broad variety of tasks that software engineers or scientists do. And then the final one is scaling number three for RL-based training. So if we're able to train models using evaluation environments, how do we get lots and lots of high quality data? So I think that's about time. That's all I had for today. So I'd be happy to talk and have any discussion about any of these topics.
All right. Thanks, Graham, for this very thoughtful talk. Let's actually move to the question and answer phase. So while folks are preparing for the questions, I would like to kick us off with my own question. So Graham, you work on benchmark validity, like open hands index, and also the rubrics-based critics. And you also talk about human AI collaboration, which seems to be a quite challenging problem because it's very difficult to capture human taste and preference with a single sparse outcome. So moving forward, what do you think is the biggest bottleneck? Do you think we need a more and better benchmark, and what does that look like to you? Or like we need a better way to capture the human taste to provide that rich feedback for RL training?
Great question. So I have lots of thoughts about this. The first one, this is a paper that is very recent. It just came out like 2 days ago, I guess. But we're very interested in building better user simulators. And if you have a good user simulator, basically what that will allow you to do is it will allow you to model human agent interaction and do RL training and do evaluation and stuff like that. But the problem is right now, I don't think any language model is really a very good user simulator. And we have this paper where we explicitly examined this, where we had a bunch of humans interact with agents and a bunch of user simulators interact with agents. And the user simulators were kind of very uniformly more cooperative than humans, more verbose than humans, and they had other issues like that. So basically, it makes the job too easy, like for the agent, and agents don't actually interact with humans that well. Um, so the second point is there's all kinds of different realism issues in benchmarks. For software engineering, for instance, a lot of the benchmarks we have are from open source software repositories. A lot of them are only on Python. And if you're a software engineer, um, well, so number one, if they're from open source software repositories, then it's very highly likely that the language model trained on that repository in the first place. So it's in the language model training data, so it overestimates the difficulty or overestimates the ease with which language models can comprehend that code base. Also, most code is not written in Python. The most popular language is TypeScript right now, and there's tons and tons of legacy code in Java, or tons and tons of enterprise code in Java, C++. Um, it's using esoteric libraries with poor documentation processes. It's just, like this is not a good reflection. And also, there's a lot of tasks that aren't very well covered in benchmarks, and especially not very well covered in popular benchmarks. Um, for science, one of the big issues is a lot of the AI for science work is only on machine learning, and it doesn't cover things like chemistry or biology or all the other varieties of science, physics, all the other varieties of science that we'd be interested in contributing to. And so I think there's a big breadth issue there, and the language models are certainly not nearly as good at, handling like chemistry data as they are at handling machine learning data, just because there's less of it publicly available. So um, all kinds of problems slash opportunities. So if like you want to do research work on that topic, then there's many, many areas that you could do there.
Okay, cool. Yeah, thanks a lot for sharing your perspectives. That's very helpful. So we have a hands raised. So Jai, please go ahead.
Yeah. Hi, thank you, Professor, for the really nice talk. So my question is related to you mentioned that if you provide the agent with more APIs to interact with any environment, then its accuracy like kind of increased just by increasing the number of API it has access to. So my question has like two parts. So first, like, is there like is there any my lesson that you learned like how to design a better APIs for the agent so that accuracy increases. Second, let's say you have a complex environment that agent wants to interact with. So, like, can the agent, can we design, like, the agent learn those APIs by interacting with the environment? Like, instead of designing, like, redesigning the APIs, the agent evolves those APIs, like, maybe build a Python function or something like that.
Yeah, I mean, that's kind of what we're getting at here, I guess. Like it writes a program to interact with the environment through code, and that code can be added to your set of APIs.
Yeah. But let's say the environment is a bit more complex, like, uh,
So my typical way of doing it is still very similar to this. Like this is a maybe slightly more structured way of thinking about it. Like after every task, you always send it to the critic, and the critic tries to, or you send it to a language model, and that language model tries to write an API. Um, Very often, what I will do is when I'm just doing my normal coding agent work, I will just tell it to write a program when I find myself doing the same thing over and over again, or I tell it to write a skill. Um, if you're not very familiar with like skills or plugins, I can maybe like give an example here. So we have like skills and Um, a skill looks a little bit like this. So this is like babysitting a pull request, and you have like scripts that are associated with babysitting a pull request. And um, what I do is if I find myself doing something over and over again, I will typically like ask the agent to update this. But interestingly, recently I've switched from Claude Opus to GPT 5.4 because GPT 5.4 is a lot better at instruction following. And GPT 5.4 has this interesting behavior where it like spontaneously updates agents.md. So like it will spontaneously update its instructions whenever it like has a new workflow it should be learning. And I don't know if this is good or bad. Like it might you might end up with a very bloated agents.md file, but I could also see a world where we have a good training algorithm that like spontaneously trains the agent um, to get better at doing long repository tasks. And there's even a few benchmarks. I haven't looked at them. Maintain. I haven't looked at them like extremely carefully yet, so I don't have the details. But there are some benchmarks that look a little bit um, further into like maintainable code generation, where you basically like need to create a repo that you can continue to maintain over multiple steps. So I think this is an interesting direction if you're interested in kind of like self-evolution of skills specifically for software engineering.
Yeah. Thanks so much.
All right, great. So next we have Vikram.
Yeah, thank you, Professor Graham. So I'm really excited to see the how you improve upon those code review sections, whereas like for the verification bottleneck, because when I was working on to using cloud code in the actual industry, I did observe like most of the code that is generated is bloated, and that ends up scraping from the actual as part of the code review, right? However, I have like couple of questions. So firstly, like into one of the underspecified problem when you gave to the agent, it failed. So did you observe like the reason for failure, whether the model was assuming the values or was it resulting in the syntax error or what was the reason of the failure? And secondly, did you also observe like going into the planning mode helps better than maintaining the skill as part of the like a markdown file or something? So instead of that, if I go into a planning mode and plan my problem properly, is that more efficient?
Yeah, great question. So typically the typically the agent will I think there's two things here. So typically the when you go from green to blue, this is when the agent doesn't have access to the user simulator.
Mhm.
Um, and when it doesn't have access to the user simulator, it just like doesn't have enough information to solve the problem. So we can't really expect it to solve the problem. Um, the failure modes are different for different models. So Claude will typically assume what it needs to do. Um, and just do something wrong. Whereas GPT 5.4, for instance, will typically like just stop and say, I don't have enough information to do this, so I won't do anything. And I think the latter behavior is preferable, but we didn't really capture that in this benchmark. We mostly like focused on the place where it can ask questions. The reason why green goes to yellow, we just observed that it asks questions too little or too much, typically. So if it asked questions too little, it would go into the same sort of assuming behavior. Sorry, what was the second part of the question? Oh,
So
planning mode. Yeah.
yeah, the planning mode.
So the planning mode, I think it'll help if you have access to a human. So if you can go and ask about it, and I think like also just highly encouraging the model to gather the information it needs before it starts working. Whether you call that planning mode or just prompting or training the model can also probably help with this as well.
Yeah, yeah, thank you.
All right, awesome. So Shanding, you're next.
Yeah, yeah. So thanks for Professor Graham's great talk. So the first question is about the LLM as judge. So you mentioned you can use LLM as judge for the verifiable rewards. So because there are some barriers when we use large language model as a judge. So how do you mitigate these barriers?
Yeah. So my current answer to this, which we're also experimenting with, we're also experimenting with for coding agent training as well, is to use checklist or rubric-based rewards.
Mm,
So instead of saying, is this good? For each example, we try to come up with a list of all of the requirements that need to be true in order for that example to pass. And if you're able to come up with this list of requirements, I feel that language models are reasonably good
mm.
to find the rewards. And we discuss that more in this paper.
Okay, okay, great.
Yeah.
Okay, thanks. So sorry, I have another question for the you mentioned Meta GPT. It looks like you use like a multi-agent system. So I want to know, so for the multi-agent collaboration, what strategy you use for that? Yeah, this.
So this is not our work. This is somebody else's work.
Oh, I see.
But basically, what I wanted to contrast was there's a lot of work on multi-agent coordination, but our approach is more monolithic,
Mm,
single agent.
I
That
see.
being said, there are advantages to using multiple agents.
Mm, mm,
I honestly think that right now, in most cases, if you'll get better accuracy if you don't use multiple agents.
mm,
But what you do get from multiple agents is efficiency
mm,
and also like time efficiency and also sometimes token efficiency because you can
mm,
get
mm,
an agent to do a separate individual task
mm, mm,
and not pass all of the context back into the same models. So um, I'm looking at this a little bit, but for software engineering in particular, it's often pretty hard to decompose the tasks because, one library will depend on
mm,
another
mm.
library and stuff like that. So you need to be very careful about creating a dependency graph between the tasks. So it's like you do this task first, and then you do these three other tasks, which are kind of independent. And then you take all of the results, you merge them together, and then you do this other task and stuff like that. And
Yes, yes.
it's highly, highly non-trivial.
Yes, yes, thanks. So what is the bottleneck you think for the multi-agent? Is the communication noise or some context length?
I think it's task allocation. So which tasks can you allocate to independent agents without having them conflict?
Okay, I see. Thanks.
All right, great. So we have a last question from Khadija. Please go ahead.
Thank you so much, Professor, for sharing your work. So I'm Khadija Konate. I am the lead for AI for Operation at NERSC, the DOE Main Supercomputing Center. So I am also the chair for Agentic AI for NERSC. So I'm very much interested when you said that you would love to work on AI for science. And so we have a large collection of workloads data for jobs, that AI jobs at NERSC. And so I would love to. So I have two questions. So one of my role is to build agentic system that can autonomously diagnose and operate our supercomputers. Also another aspect, another project that I'm working on is to analyze those large the workload data from AI jobs. So I would love to know what applications that of your open ends work can be valuable for this type of AI jobs for science.
Yeah, so I'm trying to automate all of my work, and my work is AI research, so I'm very familiar with this. But I feel like uh, getting agents to do kind of infrastructure engineering is something that we've actually been very successful with. We have one example on my blog, on our blog.
And also, will you share some of this presentation
Yeah,
or the blog? Yeah.
I could definitely share it. We have an explanation of how we like debug production issues with AI agents. So basically, we go have the agents dig into our logs and diagnose where the problem is coming from and fix them. So that's more on the infrastructure side. On the like AI training run side, I will say I've had mixed success. I have had good and bad experiences with having them write AI code because very often they will make mistakes, and mistakes are pretty hard to identify in AI ML code because usually the number is off by a little bit and it's hard to find. But on the other hand, I have had very good experience with them analyzing runs. So like identifying why something has broken. So, if I've written the code myself, it can go in and identify problems with it and help me fix them. So, yeah, I'd be happy to talk more about it. I'm very excited about AI for science, so it would be fun to discuss more.
Amazing. I will send you an email.
Great. Thanks a lot.
All right, that's fantastic. So we are about the time. So everyone, please join me in giving Graham another round of applause for this engaging session. And thank you everyone for your participation. Have a great weekend and see you next week.